Can I raise the pub or the pub?
Yes.
Anyway, it's not until tomorrow. What? Somebody will tell me how to get there. Okay, so this whole workshop and most of the people here are very esoteric and do very fancy things with names like Grothendieck and so on associated to it, and sort of difficult mathematics. But to me, multiple zeta values are something extremely concrete. And so I looked a little at the description, where's Herbert? Here he is, of the courses, the lectures that have already been given here, and they were most on the rather abstract side, which is of course the important side, in connection with associators and Grothendieck-Teichmüller groups and so on. But rather little has been said really on the very, very concrete level, what these things are. So I thought, especially since then I wouldn't have to learn anything new, I would talk about just those very, very down-to-earth aspects. So I'll start with how one actually calculates zeta values, multiple zeta values. So MZV or MZ, now I have to remember which way I'm doing this. So in today's lecture, I think they'll always be going up. But I may forget because I also use both conventions. So whichever way you write it, of course everyone here knows this definition, it's the sum of a product of monomials mi to the ki, where the mi's are an n-tuple of numbers, and they're taken to be increasing. That's of course what makes it interesting. If they were independent, it would just be a product of Riemann zeta values, which should really be called Euler zeta values. So this thing was originally invented, so n I'll call the depth, although it should really just be called the length of the argument, and k 1 up to kn, I'll sometimes just use an underlined k, you should imagine boldface if I had that font, which is the index. And I'll assume that it's admissible, which is the condition for convergence, which means that each ki is an integer, a strictly positive integer, but the last one should be at least 2, so that you don't end with 1 over m, which would be divergent. But sometimes one also looks at the divergent ones and does something. So these things were first studied in the case n equals 1, where it's just called zeta values. And everybody talks about the Riemann zeta function, but of course it's Euler's zeta function, which he studied originally in 1734, and he showed very famously that zeta of 2 is pi squared over 6, zeta of 4 is pi to the 4th over 90, and so on, but that there were apparently no corresponding formulas for odd arguments. And then a few years later, I'm not sure, I think 1745 or something, I've forgotten the date, he also looked at the case, wait, this is the case n equals 1, and n equals 2, which are double zeta values, were also studied by Euler, and he showed that zeta of k1, k2 is a Q-linear combination of products zeta of even times zeta of odd. So the zeta of even by his own theorem are just rational multiples of powers of pi if k1 plus k2 is odd. So the two first results about these things were both found by Euler, and they're often called Euler sums, and sometimes Euler-Zagier sums because of our well-known joint work with Euler. Okay, so that's what they are. And as I said, I want to start with the question how to compute them. So, well, I mean, the most important single fact, the basic fact which makes the whole theory interesting, is there are lots of linear relations among these things over Q. So let me start in, well, if the weight is 2, if the weight is k, then there are 2 to the k minus 2 multiple zeta values. In other words, if you fix the total weight k, which is the sum of, oh, I didn't even say, sorry, k is the sum of the ki's, and this is called the total weight. And that's the key invariant, so these things are meant to be a graded ring with grading k, although nobody actually knows that. And so there are exactly 2 to the k minus 2 multiple zeta values of that weight. So if I start with k equals 2, then there's only zeta of 2. If I have k equals 3, then you have zeta of 3, and you also have zeta of 1, 2, and so on. If you have k equals 4, then you have zeta of 4, zeta of 1, 3, zeta of 1, 1, 2, and zeta of 2, 2. So now the relations, well, this is, as it happens, as I said, it's pi squared over 6, but that's of no particular interest to me, the relation to pi. I'm talking about relations among multiple zeta values, so it's just whatever it is. Zeta of 3 is also just whatever it is, but zeta of 1, 2, this was already found by Euler. It's a special case of this result. Zeta of 1, 2 is simply zeta of 3, and similarly zeta of 1, 1, 2 is equal to zeta of 4, and zeta of 1, 3 is 1/4 zeta of 4, and zeta of 2, 2 is 3/4 zeta of 4. So up to weight 4, although we start with 1, 2, and then 4 values, there's only one value. And if you continue this, then you are led to the conjecture which I made many years ago, and which has been proved in one direction and has been discussed in these lectures here, so I won't talk about it. But that if I define dk as the coefficient of x to the k in 1 over 1 minus x squared minus x cubed, so that means that dk simply satisfies the recursion a la Fibonacci numbers, that each dk is the sum not of its two predecessors like for Fibonacci, but of the 1, 2 before and 3 before. So that means that dk grows like some number 1.3 or something to the k. So it's exponential growth, but much, much smaller than d to the k. Then the dimension of zk, which is the span of all of these, is conjecturally equal to this. So that's the conjecture I made on the basis of numerical evidence, and it's been proved thanks to the work of, well, now I don't know quite whom to say. It's Terrasoma, Goncharov, Deligne, various people, and there are now various proofs, also Francis Brown. Now there are now several proofs that the dimension of the space of zeta functions is bounded above by this. There's no hope of proving, so it's known, so this is the conjecture, and it's known that it's less than or equal to dk, and in the lower direction, the only bound that's known for any k at all is that it's greater than or equal to 1, because these numbers are non-zero. But otherwise, nobody can exclude, although certainly nobody believes, that they're simply all proportional to zeta of k in weight k. I mean, that's not something that anybody can disprove at the moment. So what do I mean when I say that experimentally I found this? So in other words, when I did these calculations, that was already many years ago, I went up to weight 12. So for weight 12, there are 1,024, 2 to the 10th values, and I computed 1,024 of them to high precision. And then what I found is that the number that were independent was only 12. So you start with the first one, then you take the next one and you look if it's a rational multiple of the first. If it is, you throw it out. If it isn't, you add it to the basis. And you keep doing that, and after a while you find that you have 12 numbers, but that each successive number can always be written to very high precision as a linear combination of those with rational coefficients. And so at least you convince yourself that the dimension is what it is. So what you actually find is here I'll just write z2 because z2 it's faster than zeta of 2. In weight 5, for the first time you have more than 1. You have the product zeta of 2 times zeta of 3 and zeta of 5. In weight 6 there are again 2. So now we can use our formula. 2 is 1 plus 1, 2 is 1 plus 1, 1 plus 2 is 3, 4, 5, 7, 9, and 12. And so here, for instance, you have z3, zeta 3 squared and zeta 6. And here you have, you have again 3 that you can write down, just products of zetas. And here for the first time, you have a mixed one. For instance, you can take zeta 5, 3. There's lots of choice, but you can take some double zeta, which cannot be expressed as a product of single Riemann zeta values or Euler zeta values. So what does such a table mean? See, when you say on the computer that you found that of these 1,024 numbers that there were exactly 12 linearly independent, what you mean is that you've proved that the number is at least 1 and at most 1,024. That's all you've proved. You haven't proved anything in either direction about the 12. Because what you do is you compute these values, these 1,024 values, to very high precision. I'll say a word about that as the next thing. Let's say to 500 digits. And then, you, as I said, you look at the first one. Well, it's non-zero, so you put it in the base. You look at the second, and you try to decide if it's a rational multiple of the first. So you divide through, and you apply the Lenzner-Lovich algorithm, or in this case, continued fractions. And you find that it's not a rational multiple of the first one, so you add it. But of course, it might be a rational multiple. You've only shown that if it is a rational multiple, then the numerator and the denominator have at least 500 digits, which is very unlikely. But of course, it could happen. So you haven't actually proved that the first two, even numerically, are independent. You've only shown that they are not dependent with a linear dependence involving relatively small integer coefficients, let's say smaller than 10 to the 500. Similarly, you continue, and after a while, you find that number 7 on your list is a combination of the first 6 with very small coefficients. But that only means that it's that combination with very small coefficients to 500 digits. Maybe if you computed 1,000 digits, that identity would go wrong. So what you actually do if you're honest, and I've learned to be honest with numerical calculations because otherwise they turn around and bite you, is that you find relations first with a given precision. So for instance, you calculate using 300 digits, and you find your conjectural collection of relations. And now you recalculate the numbers to 500 digits. And now you don't look for relations, you check the relations you already found, and they should be true to 500 digits. Now you have 200 digits of really honest verification. So one's absolutely sure that the results are true, but just that when I say that the dimension D12 numerically equals 12, there's no proof that it's either greater than or equal to 12 or less than or equal to 12. And all you know is that it's at least 1, at most 1,024. There's simply, well, the upper bound you can improve because there are identities. So having said that, let me say how you actually compute them, because it's kind of a good general culture maybe to know how to compute numbers to high accuracy. So let me, to compute them, I'm going to make new numbers. I'll fix an integer m greater than or equal to 0, and I'll put zeta sub m of k. So k is the same n tuple as before. I'm just too lazy to write k1 to kn. And this is exactly the same sum as before, m1 to the minus k1 up to mn to the minus kn. Same summation as before, except that instead of the mi's being bigger than 0, they're now bigger than capital M. Okay? So by definition, zeta 0 of k is my original zeta of k, the original multiple zeta value. So I simply am restricting the summation to tuples where all of the numbers are strictly bigger than some capital M. Now let's say that I've already done this for a given m, and I'm going to do something very odd, which comes up oftener than you would think in mathematics. We all learn in school about induction. You do something for n equals 1, and then you go from n to n plus 1, and then you can go to infinity. But surprisingly often in mathematics, there's a downward induction where you start at infinity and work your way down one step at a time. So that doesn't sound very promising because infinity is so far away that you'll never get there. And if you did get there and you go down one step at a time, you would never get to anything finite. So of course you have to know what you're talking about. And there are many connections. For instance, one paper that I once wrote was an identity among power series, and they were numbered by an index, and you started at infinity, but each of these things stabilized. So for any given coefficient, for the 1,000th coefficient, it was enough if the index was bigger than 1,000. But as a power series, you had to go all the way to infinity, and then you did a downward induction. And that's what we're going to do now. We're going to go from m down to m minus 1, because our goal is m equals 0, which is at the bottom. So I'm going to assume that I know zeta m, and compute zeta m minus 1. Well, zeta m minus 1 here, you have that m1 is less than, well, strictly bigger than m minus 1. Okay? So in other words, it's greater than or equal to m. So there are two possibilities. It might be equal to m, or it might be strictly bigger. So if m1 is strictly bigger than m, then we have a subsum of the sum where it's bigger than m minus 1, which is where it's actually bigger than m. And so that subsum is the previous value, which by induction I assume we know. But if that's not the case, then the other piece will be that m is equal to m1, which is less than sum. But if m equals m1, then m1 to the minus k1 is simply m to the minus k1. And what's left is m2 is bigger than m1, which is m. So it's simply zeta m of k2 up to kn. And so if I knew the value at m, but not just for k, but also for k reduced by 1, then I'd be in good shape. So what I actually do is I make a vector value thing, which I take zeta m of k1 up to kn, so my original value. Then I take the same thing where I have one index less until I'm left with just one index. And actually, it's a good idea to go all the way down to the empty set, which I define as 1. Zeta m of the empty set is 1. You may say, why? Well, there's always in mathematics, if you have limiting cases like 0 factorial and you want to know how to divide them, you want the same functional equations, which are true for higher values, to remain true. So we would like this to be true also if m is 0. And if m is 0, then you see exactly the same argument. If this is just k, 1, then zeta m minus 1 of k1 is the sum, and then it's this extra term is simply m to the minus k1, because it's a single term. So it's m to the k1 times 1, and therefore the only possible definition is zeta m of the empty set is 1. So in other words, I assume that I know this vector. So this is a vector in r to the power n plus 1. So let's say my depth might be 11. So this is a vector of length 12. It's something very reasonable. And m is some large number, like 10,000. So m is 10,000. And I compute zeta 10,000 of my index, which is an index of length k, and then I get zeta 9999 by this recursion. And you see the recursion, each thing, you just have to do one multiplication by m to the k and one summation. So it's O of 1 steps. So this whole thing is O of n steps. So in our case, there are 12 steps. I mean, it's n plus 1 steps. And then you get all the way down to zeta 0 of k. Well, actually even to the vector value thing. But having got the vector, then you just throw away everything except the top one. You can keep the others too, and so then you're done, because zeta 0 was the number we want. So in this case, 10,000 times 10, so a very reasonable number of steps, I've gotten my final thing. But the problem is, of course, I have to start at some big m. So what do I do to compute this one? Well, for that, the idea, let me first take n to be 1. If n is 1, then zeta m of k is simply the sum 1 over m to the k, m bigger than m. Okay? But of course, this you can do by Euler-Maclaurin. So this is the sum from m to infinity is roughly the integral. So that's 1 over k minus 1 times 1 over m to the k minus 1. I guess minus a half times 1 over m to the k, plus, I don't remember if I'll get it, might be k or it might be k plus 1. I don't guarantee. I'm not sure about that coefficient. It's just the usual Euler-Maclaurin form. But the point is that there's a perfectly good asymptotic expansion. This I shouldn't have written equal. It's only an asymptotic expansion. The coefficients here are Bernoulli numbers which blow up. So as an infinite series, this thing will diverge. But if n is 10,000, and let's say k is 3, then, so if, let's say I'm computing zeta of 3 for 10,000, then my first term will be 10,000 squared. The next will be 10,000 cubed, and so on. And so, 10,000 already to the 20th power is 10 to the minus 80. The terms are so small that if I just stop when the terms become more or less minimal in this asymptotic series, I get a very, very high degree of precision. So if m is large, then even though the series is divergent, taking, let's say, 20 or 30 or 50 terms of it will give me hundreds of digits. So if I know this asymptotic expansion, then I can just substitute in this formula, m equals 10,000, stop at some point, and I get an extremely accurate approximation to zeta 10,000 of k, and then I do what I did here and do the downward induction. So the only question is, how do you get this asymptotic formula? Well, the answer is very easy. Namely, let me take what I wrote down so that I get the formulas exactly right. The point is that zeta m of some tuple is, as I said, some power series, ak of 1 over m. So this is a power series, actually with rational coefficients. I'm always assuming that the ki's are integers, but I might as well mention that if the ki's were real numbers or even complex numbers, so you could, take, this is a perfectly good function of complex variables, the method that I'm describing would work exactly the same way. This formula is still true, and the power series would still be true. Everything would go through unchanged. So now the problems we have to know what this power series is. Well, one of them we do know. namely if it's the asymptotic, if it's the empty index, then for the empty index, zeta m of the empty index is simply 1, which is a power series, is identically the power series 1. So that's pretty easy. And now, if this thing is true, and by induction it is true, if zeta m of k has such a power series expansion, you can plug it into that. Then you insert here ak of m, here ak of a k2 up to kn of m divided by m to the k1. And here you replace m by m over m minus 1. And so what you get is the following inductive formula for this power series. That, assuming by induction that you know it for k being 1 shorter, because starting at the bottom for the empty set it's just 1, then you take the power series which you've already found, let's say the first 50 coefficients as a power series, for the index k2 up to kn, you multiply that by x to the k1, and then your power series, ak of x, will have the property the difference ak of x minus ak of x over 1 minus x is that, and you can uniquely solve that just starting at the left, one coefficient at a time, and so you immediately write down the coefficients of ak of x. So as an example, if you have just ak of x, so this is the case when n is 1, so it's up once, you start with n equals 0, which is the trivial case, and then the next case would be this. Then you get the one that I wrote down before where I said I may not have got it right, but here I'll write it correctly. What you find is 1 over k minus 1 times the sum from 0 to infinity, k plus r minus 2 over r, the binomial coefficient, br, the rth Bernoulli number, times x to the r plus k minus 1. But you don't need to know that in closed form. As I said, what you do is you put unknown coefficients starting at the left, and then you get a recursion, and you get each coefficient from its predecessor in a unique way. And this works absolutely beautifully, and you can program it. The whole program is 5 lines, and is extremely efficient. So one can really calculate these numbers. And I mean, this is not deep mathematics, but as I said, it seems to me since people talk so much about these numbers, it's worth knowing how to calculate them, and I've discovered that many people have no idea how you would actually calculate such a number numerically, because of course the multiple series itself is extremely slowly convergent. If your index had length 20 and small integers like 1s and 2s, then you would have, even to get 50, even to get a few digits, you would need 10 to the 50 coefficients or something, and you would never be able to do it. So you need to do something reasonably efficient. Okay, so I wanted to talk about relations, and there are stacks, and I don't really know where to start, so I'll just start with some and then prove some and not prove others, because I don't really have any choice. So let me give a couple of relations. So relations. Let's say systematic relations. Well, first, of course, I should talk about the two most systematic relations, which are the duality and the double shuffle relations, but I think they've been discussed at great length in this course. So one is the duality. We already actually saw an example before. I had zeta of 1, 1, 2, which was equal to zeta 4, and the coefficient was exactly 1. So you had two different multiple zeta values which were exactly equal. And that's not an exception. It's, in fact, universal. Every multiple zeta value, zeta of some multi-index k, is zeta of some other index k star. Well, very occasionally, the star is an involution. Very occasionally, k is a fixed point, and then it's just equal to itself. But usually it's something else. And the reason for that, again, I think everybody knows, so I'll just write it very briefly. You define the Greenfeld integral. If each epsilon I is either 0 or 1, then we define an integral over increasing sequences t1 less than t2 less than k between 0 and 1, and a0 of t is simply t, and a1 of t is simply 1 minus t. So you successively integrate either t or 1 minus t. These are the famous Greenfeld integrals. I know you've all seen them. And then it's just very easy to check that zeta of k1 up to kn is equal to such an I where this k is indeed the k I before. It's the sum of the i's. And what you do, you always have to start. The first one has to be 1 for convergence, because if you start dt over t, there'd be a divergence at 0. And similarly, the last one has to be 0, because if you ended dt over 1 minus t and integrated to 1, you would have divergence. So for convergence, you have a sequence of k numbers between 0 and 1, but 2 of them are fixed. The first is 1, the last is 0. That's why you get 2 to the k minus 2, the same number I said before. And now, if you simply group these into a 1 followed by a bunch of zeros, a 1 followed by a bunch of zeros, a 1 followed by a bunch of zeros, and then the length of these pieces are the ki's, then it's very, very easy to see by induction that this thing is true. So you have this famous fact relating multiple zeta values to the Greenfeld integrals. It was pointed out to me by Kontsevich. I don't know if Greenfeld had already noticed it or ever looked at multiple zeta values. But this has several consequences. This is the consequence 1, the duality. So this is this Hoffman duality, which Hoffman had discovered experimentally and not only couldn't prove, he couldn't even find a beautiful rule. He had a much more complicated description of how k went to k star in the original version, but it's very clear in this language. And that's simply because I of epsilon 1 to epsilon k is the same if I reverse the order of the epsilons and change each epsilon to 1 minus epsilon. So now the first one is again 1 and the last one is again 0. Then it's clear that this is the same integral, simply because you've replaced each t by 1 minus t and you've just taken the integral decreasing rather than increasing. It's physically the same integral. So these Greenfeld integrals have an obvious symmetry, and then if you translate that back, you get some more complicated looking symmetry. But another thing that you get is a product rule. Namely, if you multiply a zeta of k by zeta of L, where you have two multi-indices, then of course you can do two different things. And again, everybody has seen this. So one is the obvious relation. If I, for instance, if I have zeta of 2, 3 times zeta of 5, then I've here a squared b cubed, and here m to the 5th. But here a is less than b, and here m is whatever it wants to be. And so now if I put them together, then I see that a, b, and m is a triple of numbers, and there are 5 possibilities. You always have a less than b, but m could be on the left of a, or it could be equal to a, or it could be between a and b, or it could be equal to b, or it could be bigger. And so when you multiply this together, you see that if m is to the left of a, you have m to the 5th a squared b cubed, so you'll get f523. If it's strictly between a and b, you have to insert the 5 between the 2 and the 3. If it's bigger than b, you have to insert it after. And then finally, if it's equal to a, then you'll get, if m equals a, you'll have a to the power 2 plus 5 is 7. So then you have these mixed terms where you add 5 to one of the arguments. And you can do this, of course, for any two multiple zetas. So therefore, this is a sum of zetas. So you multiply the sums and reorganize the way that I just said. But it's also another sum of zetas where you multiply the integrals. So you do exactly the same thing with the Greenfeld integrals. You replace zeta of 2, 3 by its Greenfeld integral, which is I of 1, 0, 1, 0, 0, times I of 1, 0, 0, 0, 0. And now you multiply and you do exactly the same thing with the two integrals. You have t1 less than t2 less than so on, u1 less than u2 less than so on. When you put them together, then the t's and the u's, there are various possible orders, and so you get a finite collection of values. And so that's the basic story of the shuffle relations, which I've said very quickly because I know you've all seen it. We get two different ways, two different proofs that the space spanned, let's say, over z or over q by the multiple zeta values is a ring, namely that the product of two zetas is an integer linear combination of zetas. But you get two completely different expressions, one by multiplying the sum, one by multiplying the integral. And if you equate them, then since they have to be equal, you get a non-trivial identity. And the conjecture is that these identities, if you enlarge them by also allowing certain divergent products, and you have to renormalize, and I don't want to go into it, then you get some more identities. It's the same principle, but using the divergent sums. And then the conjecture, which is completely open, is that that's a complete set of relations. But it's certainly true up to quite large weight. So that's the first set of relations. So here I've put so this is the duality, which is this one. And this is the shuffle or the double shuffle relation, or shuffle and shuffle. depending on your taste. So those are the ones I don't want to talk about, and I want to talk about sort of individual, nice other relations. So, well, first there's one connection which is more or less trivial. Certainly this was known very well to Euler, which is that if you, so one fact is if you take always the same, well, I'll call it k, but it's not the same as the k before because the previous k was the sum. If all of my arguments are the same, then this thing, so let's say I've n times k, then this will be a combination over, well, it'll be in the algebra generated over q by the Riemann zeta value, so the Euler zeta value, zeta of k, zeta of 2k, and so on. So this is nearly a triviality. So example, I'll call it proposition, but this is really easy. So example, if I have 3 of them, then you get 1/6 zeta of k cubed minus 1/2 zeta of k, zeta of 2k. Actually, people who do intersection theory on moduli spaces will have seen this formula for the kappa classes and tau classes of Witten. It's the same formalism. So zeta of kkk is this sum, and the proof is, you just think about what it says. This says 1 over a to the k, b to the k, c to the k, a less than b less than c. So this is this, which is nothing else than the third symmetric polynomial of the infinite collection of numbers 1 over n to the k, right? And then you can write that, of course, in terms of powers of sums, like Newton sum. So I mean, this is almost a triviality. Well, let me actually give the formula just because I want to show how you use, I mean, this is, as I say, you can do any case by hand just like that. But the actual formula is that if I take, well, since I already made the convention that zeta of the empty set is 1, I didn't have to separate this, but now I did it. I could have included this in the sum, just started at n equals 0. So if I make the generating function of all of these, then it's simply the sum n from 1 to infinity minus 1 to the n minus 1 zeta of kn x to the n over n. You just exponentiate that. Okay? And so the proof is just what I said. This was, remember, the nth symmetric product of nth elementary symmetric function of 1 over 1 to the k, and so on. So therefore, this whole thing is simply the product n from 1 to infinity of 1 plus x over m to the k. Because if you multiply that out and look at the coefficient of x to the n, it will be the nth elementary symmetric polynomial. And now all you have to do is you write this product as the exponential of the sum of the logs, and then the sum of the logs you just interchange. You expand the log of this as a series and interchange with the sum, and you get the Riemann zeta function. It's a one-line calculation. Yeah?
Is it coincidence that it strongly resembles the Veneziano amplitude?
No, it's not, and I'll come to Veneziano later. Thank you. So, I'm not entirely sure if I know what the Veneziano amplitude is, but I have a formula connected with the Veneziano amplitude that I'll come to later, and then that should answer your question. So I want to stay on this in a more explicit case. So if k is even, then of course, if we combine this with Euler's result, then you find that you just get a rational multiple of the power of pi, because it was a polynomial in Riemann zetas. Euler zetas, it's zeta of k, 2k, 3k, but if k is even, so are all the multiples of k, and then you get these powers of pi. So how about if k is 2? It turns out that's kind of amusing. So, no, not just if it's 2. 2 is actually very boring. If it's 2, then you get this explicit formula, which is completely trivial because you just do what I said before, and you find that the sum zeta of 2 to n times, actually it's a little more convenient to put minus x squared to the n. This is, by what I just told you, the product, well, it was 1 plus x, but I've changed it to 1 minus x squared over n squared, and this is, of course, sine of pi x over pi x, also by formula of Euler, and so you just expand sine of pi x also by formula of Euler, and you find this. But then the amusing thing is you can do this for k equals 4. Then you'll get a similar thing, but you'll have x to the 4th over m to the 4th, but that factors as x squared over m squared times 1 plus x squared over m squared, so it's something with sine and sinh, and you can expand that with cos, and so you get a perfectly good formula also for 4. And then what's kind of amusing, it has no mathematical depth or significance as far as I know, but so here's the formula for zeta 4 n times, and similarly if you take 6 n times, I'm not writing the n each time, but it's always n, it's 6 times 2 pi to the 6n over 6n plus 3 factorial. But then if you continue, for instance, if you do 8, then there's a slight surprise, because this one is 2 to the 6n plus 2 pi to the 8n, and again there's an 8n plus 4 factorial. But now the numerator is a Fibonacci-like number, and it's something that satisfies the recursion, two-term recursion. And what it is the trace of the square root of 2 plus 1 to the power 4n plus 2. And similarly, there's a formula for every k. If you want, I can write it down just for fun. This entire talk is just to have fun, because there's so many serious talks. I thought one should have one that isn't. And so I'll write down the general proposition. If k is k and n are positive integers, but I've changed my notation, so this is now zeta of 2k, so it's indeed even because I've called it 2k. Then the formula is 2 pi, well, the power of pi that you expect, 2 pi to the 2kn over 2kn plus k factorial. And then it's going to be a finite sum depending only on k. So when k was 4, there were 2 terms in this sum, but in general there'll be lots and lots of terms, but it's a finite sum. Namely, I sum over lambda 1 up to lambda k, and each lambda j is a kth root of 1, but it's a particular one. It's either e to the pi ij over k or minus e to the pi ij over k. So there are 2 possibilities for each lambda j, and therefore the sum will have 2 to the k terms. And then you take the sum of these lambdas. I'll drop the proof. You can do it for yourself just using what I already told you, and it's completely easy. It's the sum of these lambdas to the power 2nk plus k divided by the product of these lambdas. So it's a finite sum of some algebraic numbers times algebraic numbers to the nth power. So it always looks like the one for k equals n. So, okay, well, I'll give you one cute formula. If I specialize down to the case when n is 1, here I was letting k get bigger and bigger. K was 1, 2, 3, 4. But if I let k be arbitrary here and n to be 1, then I get a kind of a cute formula for the Bernoulli number. B2k, at least I've never seen this before, and it's vaguely amusing. You get minus 1 to the k minus 1 times 2k factorial over 2 to the 3k minus 2, 3k factorial, and then the sum, well, the same lambdas as I just had. I mean, I'm just specializing, so it's not very surprising. But you get this rather amusing formula as a finite sum of algebraic numbers to the power k, and similarly you get one if n is 2 or 3, you get higher formulas. Okay, so these are formulas of 0 depth, not in the technical sense, but I mean they have, the reason is that I say this is 0 depth. The whole point of multiple zeta values is that you have, for instance, m less than n, and that's what makes it hard. If I summed over all m and n, you would just yawn. Well, but if you think about it, if I had here m cubed and also n cubed, then it doesn't matter if m is bigger than n or less because I'm doing the same thing. So in other words, by making the arguments equal, I'm killing the whole interest of multiple zeta values because it now doesn't matter which one is smaller. All that I'm doing is I'm subtracting the terms where they're equal, and that's why I get these trivial formulas. So these formulas are in a sense fake. They're true, but they're of no interest from the point of view of multiple zeta values. Because there are cases where it was already clear that everything could be expressed in terms of Riemann zeta values. I mean, there's no interesting inequality m1 less than m2. So now I want to come to slightly more interesting ones. So I already mentioned that Hoffman had numerically discovered this duality, which at the time looked mysterious until it became completely trivial because of the the relationship to the Drinfeld integral, but he also noticed the sum formula. So I'll call it theorem. So this was conjectured by Hoffmann, and then it was proved independently by Granville and myself, and I'm sure by other people since then. It's not particularly hard. And this claim is for all k. So k, the total weight, is always bigger than n, because remember, k is the sum of the ki's, and n is the number of ki's, and each ki is at least 1, but one of them is at least 2. So k is always strictly bigger than n. You have that the sum over all k with the given depth, so length, if you wish, n, and weight, k, of zeta of kn, zeta of k, this thing is always not just something expressed in terms of Riemann zeta values, it is simply zeta of k with the coefficient 1. So that's an extremely simple statement. So at the beginning, I gave examples for zeta of 3. So for zeta of 3, there are only two possibilities. The length, the depth can be 1 or 2. For zeta of 4, the depth could be 1, 2, or 3. And then here we had zeta 4, well, times 1. Here we had zeta 4 times 1, and these two were, I think it was 3/4 and 1/4, or maybe the other way around. So is it this way or the other way? Somebody will remember, or just taking notes. Anyway, whichever way it was, the sum of these two numbers is 1. So you see that here we have three possible values. The depth can be 1, 2, or 3, but in each case the sum of the coefficients is 1. So that's the general statement. And I'm wondering if I should... Sorry? It is the other way around, thank you. Yeah, there's actually a general theorem that was proved in a paper by Herbert, Gangel, and Kaneko and me, which is that if you have an even total weight and you take the, you take the double zeta values, then of course the sum of all of them is zeta of k by this result. You can take the ones where both arguments are odd or both arguments are even. And then it turns out that the sum where both arguments is odd is always 1/4 of the total, and the sum where they're both even is always 3/4 of the total. So that's another general relationship. So I don't know if I want to prove this or go right ahead to the more do I want to? No, my original proof of the sum thing is too complicated, so I think I'll skip my proof. But then there was a theorem that I proved with Yasuo Ono several years ago, which is similar, which says that if you fix the sum of all of the zeta of k's, and you fix the depth is n and the weight is k, and then the last thing we call the height, which I'll define in a second. So the height is the number of indices ki which are at least 2. So in other words, it's the number which aren't simply 1. So you trivially have you have to have n greater than or equal to s greater than or equal to 1, and k is greater than or equal to n plus s. Otherwise, there aren't any multiple zeta values with this weight and height and depth. So that's the conditions for admissibility for these three numbers. And so now the theorem was, if I fix, so let me call this set I0 of nk and s, k, n, and s. I want to stick to the notation of my paper with Ono. So this is the collection of k's with a given depth. So it's length n of the vector. The sum of the ki's is k, and the number of ki's which are not 1 is s. So the number which is 1 is, I guess, n minus s. And then you define g0 of k and s to be the sum. And the claim is that this is still a polynomial over Q in Riemann zetas. Okay, I'll write it like that, and then I'll give the complete formula in a second. It's a little hard to write on this board underneath the other board. So let me give the complete formula. So the way to do it this I want to go through the proof more or less completely, or sketch it, just because it shows, and this is the basic technique to do all of these things, is a combination of hypergeometric functions, expansion of the gamma function, and the use of generating functions. So this particular identity sort of illustrates them all. So if I put all of these numbers, g0 of k and s, together into a single generating function, then since k is at least n minus n plus s, I can take x naught to the power k to the power k minus n minus s, and similarly s minus 1 because s is at least 1, and y to the n minus s because n is at least s. So this will be some power series in 3 variables, x, y, and z. And the claim is that this entire power series can be expressed in terms of the Riemann zeta function. And so the theorem says, so this is the definition, and the formula is slightly confusing formula. It's 1 over xy minus z. You can write it in another form, I'll do that in a minute, but this is the useful one. You take 1 minus the exponential So I'm going to define certain polynomials, Sn of xyz, which will be homogeneous of degree, I think, just n. And I'll define them in a second. And then you take the exponential summary of these polynomials, which are polynomials with rational coefficients, multiply by zeta of n over n, sum over all n, exponentiate, subtract that from 1, and divide by xy minus z. So the S is defined as x to the n plus y to the n minus alpha to the n minus beta to the n, where alpha and beta are the two numbers whose sum is x plus y and whose product is z. So by solving the quadratic equation, they're given by x plus y plus or minus square root of x plus y squared minus 4z over 2. So, and you can also, if you like, if you prefer generating functions, which everybody does, then you can also just say that you take the log of this simple rational function, expand it, and then Sn over n is the degree n part of that. Okay, so this is a completely explicit formula. It's not particularly exciting as a formula, but as I said, the method is typical of what you use to prove many, many identities of this sort, so I thought I would give the one example in some kind of detail. But now I have to follow the notes because I certainly can't remember it by heart. So the basic idea is this. So if I have a multi-index k as k1 up to k2n as before, then what I do is I take my multiple zeta value, but I weight it. So this is some kind of a multipolar logarithm. I weight it by inserting a factor t to the mn, t to the power mn. Okay? So by definition, therefore Lk of 1 is simply zeta of k. So this is a crucial idea which you use in the whole theory, that you insert this thing. So here, let's say originally t is less than or equal to 1, and now it converges. If t is less than 1, it converges even if the ki's are no longer admissible. It no longer makes any difference. And let me also make a slight thing. Okay, so if I will be exactly the same as before, but now I allow that S is 0. Okay, so now I can do the same as we did before, make a generating function. I sum this all up with k in this set I of k and s. Well, I have g and g0 with I and I0. I0 is what I had before, and I is the same where I allow s to be 0. So don't worry too much about details. If you really want to check them, the paper's written and published. So we have two, you see, before S wasn't allowed to be 0. Because to say that S is 0 means that there are no ki's which are equal to 0. So all of the k's were at least 1, and the last one for convergence, I needed 1. But once I have this t, now the ki is allowed to be 0. So now I can have this larger set, which I'll call I, which is the same conditions as before. K greater than or equal to n plus s, n greater than or equal to s, but now s is allowed to be 0. So I allow myself slightly more freedom. And so then I have this, and I can make the same generating function as before. So I have a phi of x, y, z, and t, just by the same generating function as before, but with these new things. Okay? So let's look explicitly how it looks. So phi will start 1 plus L1 of t times y plus L1 comma 1. So this is the 1, 1 logarithm. So it starts like this, and phi 0, which is the one with the initial conditions where s is at least 1, will start L2 of t. So L2 of t, remember, is just the sum t to the m over m squared. So it's the usual dilogarithm. And then the next one would be the 1 comma 2 dilogarithm. So this is sum 1 over m to the 1, m1 to the 1, m2 squared times t to the m2. So we have these two series. This is the one that we're interested in, the one that corresponds to convergent things. In other words, at t equals 1, only this makes sense, because these things all have to converge. But if t is less than 1, then you can deal with the other series. And now comes the point that if you differentiate Lk of t, then what happens? Well, when you differentiate, you get simply 1 over t, and the last index is reduced by 1, because, after all, you have t to the mn, and when you differentiate it, you get mn times t to the mn minus 1, so the minus 1 is this, and the mn reduces kn by 1. However, this will only work if kn is at least 2, because I haven't defined these things if the last index is 0. So if kn is 1, if the last index, which is now allowed, for my multiple zetas, the last index has to be at least 2. But for these t things, there's no restriction. So here, I have a tuple, and each ki is at least 1. And there's no particular restriction. If the last one is 1, then when I differentiate, I'll have t to the m over m. When I differentiate, I get t to the m minus 1 over nothing, just m to the 0. But then I can sum that geometric series. And so what I get is simply 1 over 1 minus t instead of 1 over t, times Lk1 up to kn minus 1 of t. So you have this completely... Sorry?
Excuse me. What is the difference between the generating function g and g0?
Yeah, so the difference is that g... First, this is not a generating function. This is a finite sum. This is just, I collect all of the multi-indices in this given set, weight k, depth n, height s. Here I do the same with the set I0. And so I said it, but I didn't write it. I0, the ends are at least 1, but here I allow 0. So it's a slightly different set. So that's why we have two slightly different things. But it's a detail, and just ignore it. I just want to show the essence of the proof, but for completeness, I wrote everything. So this is the key point. And by the way, this is what gives the Greenfeld integral, because then this exactly tells you that zeta of k, which is Lk of 1, you see, this will tell you that Lk of t is the integral t1 less than t something less than t, just by induction, and then you divide dt1 over 1 minus t1, dt2 over t2, or 1 minus t2, etc. At each stage, you have either dt over t or dt over 1 minus t, depending whether that ki is 1 or not. You keep reducing the k till it becomes 1, and then you have a 1 minus t. So this is exactly the proof of the equality that I gave you before with the Greenfeld integral. If you just write down this thing, then you can successfully integrate. So now the point is that if I use this thing, so this is the trivial property of the derivatives of these higher polylogarithms. But now I take this g of knst, or the g0, with the indexing set, that's a finite sum of these, so I can also compute the derivative. And when I do it, I get, well, I can write out the whole thing. It's a little of a bore. It's k minus 1, n, s minus 1, and t. And then g0. It's all very boring to do this carefully. Don't try to take notes on this. I suggest if you care, just ask for a copy of the paper. It's all written there. But the point is that you get a formula for the derivative both of g0 and of g minus g0. The other one is, so this is again knst, and it's even simpler. This one I can write out. So you simply, by applying these two formulas and then summing over all possibilities, that's a finite sum of given weight and depth and height, then you find that the derivative in t of g0 is a combination of the g's, and the derivative of g minus g0 is a combination. So you get both derivatives. And now if you want, you can, now you can make the generating functions. So these capital phi, which were the generating functions, the same as I did for the, it's the same generating function as this phi 0, but I put in a t because I replaced g0 by the thing with a t. And then you find the exact same thing that d phi 0, well, I should put partial, but I think of x, y, and z as just parameters, so they're fixed. The derivative of phi 0 in t is phi minus 1 minus z phi 0 divided by yt plus x phi 0 over t. And the derivative of phi minus z phi 0 by dt is y over 1 minus t phi. Okay, so now if you eliminate, you get, if you eliminate phi, you get a differential equation for phi 0, and that solution, well, you could just write it down because it's a second order differential equation, and it turns out just to be the hypergeometric one, and so the answer turns out with the same alpha and beta which I defined before, which I think of, you know, they're still here. Alpha and beta are these two strange expressions. Then you find this rather remarkable formula that the entire generating function, simply because it satisfies the second order differential equation with, and it starts out with, you know, I gave the first couple of terms, then you can solve it uniquely, and it's simply, after a small change of variables, it's just a hypergeometric equation, and so it's just a hypergeometric series. And so now, when you have that, well, now we're almost done, because now we get that if I set t equal to 1, which is what I want, that's the original one. So if I set t equal to 1, I no longer have polylogarithms, but simply multiple zeta values. But now, and that's where I said this is something that comes up in many of these calculations, we pass via hypergeometric functions because we use a differential equation. But once we've got the hypergeometric function, we now specialize to t equals 1. But for t equals 1, what you get, let me multiply out because it's easier, then I don't have to put a denominator. If I multiply this by x, y minus z and subtract 1, then I will get f of alpha minus x, beta minus x, 1 minus x, and 1. But by Gauss's formula, I think it's also due to Euler, that can be expressed as a quotient of gamma functions. Okay? And now finally we're done because we use the very well-known fact that gamma of 1 minus x is e to the power of the Euler's constant times x plus the sum zeta of n x to the n over n from 2 to infinity. And so if I insert that in gamma of 1 minus x, 1 minus y, 1 minus alpha, 1 minus beta, I get something involving only the Riemann zeta values, except we have Euler's constant, which you never want, but it's multiplied in the exponent by x plus y minus alpha minus beta. But as you can see from here, alpha plus beta is x plus y. So the Euler's constant drops out, and you're left with exactly what I said. So that's that proof. And as I said, it's one of many, many formulas of the same type. So let me give one other, simply because it's Veneziano and the question was raised. Well, maybe before I do Veneziana, I should do one other easier one. So you said I have sort of an hour and a half, so I still have some time, right? So then maybe before I do the Veneziano, I'll do one other nice one, which I particularly like. So I showed you before formulas, for instance, 6666 n times. So long ago, when I was first playing with these things numerically, then I tried other combinations that were periodic, but not just repeating the same number. And none of them worked, but one that I just found in my tables of numbers, and then I checked a whole bunch of values, was that if you took 1313 n times, so the total length is therefore 2n, because I have n pairs, 1, 3, so that means that the weight is 4n, and the depth is 2n. Then what I found experimentally was a very, very simple formula, just as simple as the one for 2222. So it's a pure power of pi times 2 times a factorial. So exactly similar to the other formula. But I couldn't prove it at all. And then Broadhurst gave a beautiful proof, and I simplified his proof a little, so I'll give you the simplified version, which was later published in a paper by 4 authors, the simplified version. But this is really Broadhurst. So this is, I say, is a formula that I've conjectured based on numerical evidence, just that in my tables I noticed that 1313 and 131313, which were in the left of my tables, did this, and then I calculated a bunch more, and it always worked. So here's a theorem, I say, with a very, very pretty proof due to Broadhurst, except that I simplified it even a little bit more. Okay, so that's the claim. Well, actually, this is going to be the corollary of, so this is, well, okay, it is a theorem, but it's going to be implied by a theorem that really is his. I mean, this one, I'd found the theorem, I just didn't find the proof. But what he discovered is that if I take the corresponding polylogarithm, so the one that I just explained, it's still written on this board, so you take exactly the same thing, a less than b less than c, a, b cubed, c, d to the cubed, and so on, but at the last one you take t to that power. And now you make except I did something terrible. Well, I have to call it t because I called it t, but in my notes it's called x and the other one is called t, so I'll call this one u. I make a generating function where capital X is going to correspond to the weight, so since the weight of this thing is 4n, I take x to the power 4n. And the claim is that this is simply the product of the usual Gauss hypergeometric function, so f, a, b, c, x, I think everyone knows what it is. And the arguments are very special. It's going to be f of a minus a, 1, and x. So the 3 arguments, the f, a, b, c of the hypergeometric function, the first 2 are negatives of each other, and I don't call them t and minus t, but t over 1 plus t and minus t over 1 plus t. The next one is 1, and the next one is but now I really have a problem because I'm interchanging t and x. Maybe I just can't assume I'm smart enough to do this in real time. So I'm sorry, but I called t before is now called x. But anyway, it's just a definition. But then at least I can follow my notes. And now you multiply 2 hypergeometric functions. So the other one is exactly the same, except that it's, sorry, this is not t over 1 plus t. That's because I'm nearsighted. It's 1 plus I and 1 plus I. But of course that has complex coefficients, and this is real coefficients, so I better take the complex conjugate. So it's with 1 minus I and minus t over 1 minus I. So of course these 4 numbers, 1 plus I, 1 minus 1 plus I, 1 minus I, and minus 1 minus I are the fourth roots of, whatever the fourth roots of, minus 4 I guess. So that's the formula. So the proof is, this is going to be 1 line, but you have to think of it, you see. So the sides is both sides, I'll write out the entire proof. Both sides belong to 1 plus x squared c of x. So both of them are power series in x. I want to think of them as a power series in x, even though I've written in t, but remember this is also a power series in x. So they all start with 1. That's true. Well, here, of course, it's clear because f is a power series and it starts with 1. So f of ABC starts 1 plus AB over C, but if C is 1, it's just ABX. But here, AB is minus t squared over t squared. Here, it starts 1 plus lambda x plus higher, and this is 1 minus lambda x. So together, it starts 1 plus O of x squared. And the left-hand side trivially does that too. So both are power series like that and are annihilated by, and now remember this thing where unfortunately my t has become x. When you go down from k to k minus 1, if you apply the operator t d by dt, in the first case here, you reduce the last index by 1, and you keep doing that until it becomes 1. But then you have to apply the operator 1 minus t d by dt. So if you have the thing 1, 3, 1, 3, n times, then if I apply to it t d by dt once, then I will have 1, 3, 1, 3, and the last will be 1, 2, because I've reduced by 1. If I apply this a second time, I'll have 1, 3, 1, 3, and the last will be 1, 1. But now, because it's 1, I have to apply the other operator, which is 1 minus t d by dt. And when I apply that, I will reduce the 1, 1. I'll just throw it away. So I'll first have 1, 3. Then when I apply t by dt, I'll have 1, 2. When I apply t by dt again, I'll have 1, 1. But then when I apply 1 minus t d by dt, I simply remove that last one. And when I apply 1 minus t d by dt again, I remove the last one. And so if I do these 4 differential operators, t d by dt twice, followed by 1 minus t d by dt twice, where it was t here, but now it's x. Then, all that I've done when I apply this to L1313 n times is that I'm left with L1313 n minus 1 times. But if I have the sum, well, for n equals 0, it's just gone. And so now it's n minus 1, so renaming n to n plus 1, it's the same L1313 n times, but now it's t to the 4n plus 4. But that's simply t to the 4th times what it was before. So therefore, this differential operator, the product of those 4 linear operators in x, minus t to the 4th, annihilates this. But the hypergeometric function has a well-known differential equation of degree 2. So of order 2, so if you multiply 2 of them, it satisfies the 4th order equation. You just work out what it is. And that's the miracle of what Prof found. You find that it's the same operator. But it starts with the same terms, 1 plus O of x squared, and therefore it's unique. So that's the end of the proof. It's a one-line proof. And the corollary is now immediate, because now when you take, well, now I can give the corollary. So that implies now that the sum zeta of 1, 3, 1, 3 n times t to the 4n, so I simply set x equal to 1, then I will get the product where x is now 1. But now I again use Gauss's formula. So Gauss's formula tells me that f of a, b, c, and 1 is some product of gamma functions. But in the special case, when it's a minus a and 1, it's really easy, because it's just 1 over gamma of 1 minus a times gamma of 1 plus a. Now we use Euler's formula. This is simply sine of pi a over pi a. So therefore, if I insert this, then I simply set x equals 1 in this formula, then I will get sine. On the right-hand side, I will get 2 over pi squared t squared times the sine of 1 plus I over 2 pi t times the sine of 1 minus I over 2 pi t. And of course, you can use now the formula you use in high school, learned in high school for a product of 2 sines is difference of 2 cosines. And what you get is hyperbolic cosine of pi t minus ordinary cosine of pi t over pi squared t squared. And now if you just compare coefficients, then you get this thing with the factorial. So it's an extremely short proof, but very clever. We use once again the zeta values. So what I'm saying is that the numerical way to prove relations among multiple zeta values, or at least one that works in many, many cases, is to first insert this variable, which I unfortunately changed the name from t to x. You insert the variable, so you make these numbers into the special value at t equals 1 of a power series, which is a higher polylogarithm function. And those higher polylogarithm functions are much simpler because they satisfy various trivial differential equations. The derivative of each one is just a multiple of a previous one. And so that uniquely defines them by induction. And it means that given any expression, if you're lucky and the expression has a reasonable form, you can prove the reasonable form because you have a differential equation. So of course you have to write down the right one. If I put 1, 5, 1, 5, it won't work. There is nothing. But if you're lucky, if there is an identity to be found, then the proof is really easy because once you know what you're looking for, the fact that each of these L, K1, K2 up to Kn of x satisfies its derivative as the previous one means that this function of two variables satisfies a differential equation. And so if you're lucky, you can just identify the solution. And then if you're very lucky, and that's what happened in these two examples, the solution is in terms of hypergeometric functions whose argument is the same x as this x which was t. So when you go back to the multiple zeta values, you're left with the hypergeometric function at 1. But then by Gauss's formula, that's just a product of gammas. And then for gamma, we use this fact that is well known, that the gamma function expanded around x equals 1 involves Riemann zeta values. So I wanted to give maybe two more examples in the remaining time. And I'll give, so the first will be this Veneziano one. In a sense, it's completely random. I'm not saying it's a particularly interesting identity, except that it came up in a calculation. It's a string amplitude calculation. It was shown to me by Pierre van Hove and Michael Green, so very reputable string theory people. And it's also slightly amusing, so I won't give every detail, but since I did this several years ago, partly based on some numerical calculations with Herbert, so we found, sort of guessed the formula together, and then I gave this analytic proof. But there's something slightly perverse about the formula, and since I like slightly perverse formulas, I thought that's a reason to give it too. So I'll first describe what we're doing. So this is the Veneziano function. So for the non-physicist in the audience, Veneziano, who's now one of my colleagues in Paris, was the inventor of string theory, one of the inventors in the first round of string theory when it was in, before it became, when it was applied in a completely different area of energy levels and didn't work in the sense that it contradicted all experiments and couldn't be a physically good theory, but it was mathematically a fine theory. And then it kind of died for 25 years and then got revived with the work of Green and Witten and Schwarz in modern string theory. But Veneziano was sort of the original person. And so I'll just write down a function that there are several functions associated to his name, and this isn't quite the usual, the standard one, but I'll do it anyway. So let me write x to be the set of triples, three complex numbers with some 0. So it's just isomorphic to C2, but and I'll call the variables x, y, and z. So these are three complex numbers with some 0. And now I'm going to define v is going to be a meromorphic function on x. So here it is, v of x, y, z, v for Veneziano. Well, I'll first write it's an infinite product because it's kind of cuter. So x, y, and z are actually not going to play a role directly, but as the roots of a cubic polynomial. So I'm really interested in the polynomial n plus x times n plus y times n plus z. Now that cubic polynomial, you'll notice, starts n cubed, and then luckily the coefficient of n squared is 0. Because x plus y plus z is 0. And downstairs I have the same with minus x. So it also starts, the numerator is, the denominator rather is also n cubed plus 0 times n squared. And so when I take the quotient, it's 1 plus O of 1 over n squared. And so it converges. So if x and y and z did not have the property that their sum were 0, these infinite products wouldn't make sense. Of course, you could renormalize them by putting in a factor e to the 1 over n times x plus y plus z. But I don't have to do that now. So now if you use the well-known expansion of the gamma function is the unique function which has poles at non-positive integers, and it's got a standard product expansion. If you use that, then you'll find that you can write this infinite product as a finite product, but now as transcendental functions. Like this. Okay, so here you have this nice function. So properties, so it's symmetric, in the three arguments, so S3 symmetry, V equals 1 if X, Y, Z equals 1. Let's check that. So I have three variables, their sum is already 1. Let's assume that their product is 1. Then I don't believe what I just wrote, even though I copied it very carefully from what I typed, but it's got to be 0, I think. That makes much more sense. So if x, y, z is 0, then one of them is 0. You'll grant me that. So let's say z is 0, but since the sum of them is 0, then x equals minus y. And so if x equals minus y, I have 1 minus x times 1 plus x over 1 plus x times 1 minus x, and that's 1. So this looks better. Sorry, what I wrote before was nonsense. That was a misprint. Then another property is there's a functional equation. If I change x to x plus 1, then it changes in a trivial way, because after all, it's a gamma function, except that I'm not allowed to change x by x plus 1, because my function is only defined where the sum of the variables is 0. And so if I increase x by 1, I better decrease y by 1. But then I haven't changed z, so in this thing I haven't changed the last one, but I've changed x by 1, and I've changed, therefore, 1 minus x by 1, 1 plus x by 1, and 1 minus y, but gamma functions have a simple factor, so you immediately get the formula, and it's this. So these are all totally trivial properties. Then another property which is even more trivial is if you change the sign of x and y and z, then you just invert the thing, because from either formula that's clear. And finally, it has simple poles. For x equals n, or y equals n, or z equals n, where n is a natural number. That's simply because here they are. You see that x is n, y is n, and z is n, and simple zeros if x is minus n, y is minus n, or z is minus n, again with n. And again, that follows immediately from the thing. Okay, so this is the function. And now I want to expand this as a power series. So I want to write this as a power series, but it's obviously symmetric. I mean, I read that was my first property. It's symmetric in x, y, and z. So let me introduce new variables. Well, capital X would be the sum of the things, but it's 0. But then capital Y is minus the second symmetric function. So that's x squared plus y squared plus z squared over 2. That's not the definition of the symmetric function, but because the first symmetric, the sum of the variables is 0, this is true. And you can also write that without a denominator, but less symmetrically. Remember, the three variables, 2 of them determine the last, because x plus y plus z is 0. So I can write it like this. And z is sigma 3, which is x, y, z. Or if I want to use just 2 of the variables, it's x minus xy times x plus y. So obviously, this v is going to be a new function. So then v of x, y, z is, of course, also a function of these new variables, capital Y and capital Z. Because of the S3 symmetry, it's got to be a new meromorphic function. And now it has poles if Z is minus ny plus n cubed, and zeros if Z is equal to plus ny minus n cubed, where again n is a natural number. That's just translating what is written there. So in other words, in these new variables, now we only have 2 variables, because the sum of the 3 was 0. And then, I mean, I can't do this, but z will be along certain lines. Z is a multiple of y plus n cubed. There will be poles, and along other lines there will be zeros. Okay, so now we want to expand this thing. So the first fact is trivial, and so here's proposition. Well, the only slightly non-trivial thing is where it converges, but you just ignore that. Then this v tilde. Remember, v tilde is just the same as v, but in the terms of these new variables. Then we can write it as the sum over 2 times the sum over integers p and q greater than or equal to 0. Q is odd, so actually it's greater than or equal to 1. And then it's the binomial coefficient p plus q minus 1 over q. Riemann zeta of 2p plus 3q times y to the p times z to the q over q. So in particular, this thing is 2p is always even and 3q is always odd because q is odd. So what this says in particular is that this is a power series in y and z, as it had to be, because it's meromorphic, but near the origin it's not got a zero pole, so you can write a power series, and the coefficients are all polynomials in odd Riemann zetas, so zeta 3, zeta 5, and so on. So the proof of this is totally trivial and totally boring. And also there are no multiple zeta values, because these are just ordinary zeta values. So let me give the proof. If n is a natural number and n times y plus absolute value of z is less than n cubed, which will certainly be true for every natural number n if y plus z is less than 1, then I just take the expression on the left, but I take only the single term, n plus x, n plus y, and n plus z. And so if I multiply this out, well, this is just a cubic polynomial. The linear term is 0. The quadratic term is 0. The linear term is minus y, and the constant term is z. And downstairs, it's the same with minus z. So therefore, just by the usual formula for log, you get the sum, 2 times the sum, q greater than or equal to 1, q odd, 1 over q, z over n cubed minus ny odd. And now you just expand this sum over p and q, q odd. And when you expand this by the binomial theorem, you get n to the power 2p plus 3q. So that's just a one-line identity. And now you sum this over all n. And so here you get the log of the product, which is the Veneziano sum. And here the sum over n gives you a zeta value, zeta of 2p plus 3q. So that's a one-line proof, and there's absolutely no difficulty. And, so that's it. So in other words, we can write this thing as the sum EPQ, y to the p, z to the q. And then, as I said, each EPQ is a combination of Riemann zetas, a polynomial in Riemann zetas. So why is this interesting at all? And why am I talking about it in connection with multiple zeta values? And here's the perverse thing. You see, usually what you do in this business is you have some multiple zeta value, like this one, and then you want to write it as zeta to the 4 to the n times a rational number. In other words, you want to reduce multiple zeta values to usual Riemann zetas. Another example would be my theorem with Ono, where we took the sum over all multiple zeta values with given height and depth and weight, and we believe those are complicated things, but then the sum was a combination of Riemann zetas. So the usual philosophy is Riemann is easy, it should be Euler, and multiple zeta is hard. But here we're going to do the opposite. This was a 2-line calculation. It was extremely easy, and we found that these coefficients, which are the ones that physicists want, the EPQ, these are the amplitudes that play a role, they are expressible in terms of Riemann zeta values. But when you multiply out this expression, they're extremely complicated. And so let me give a couple of examples. So what you find, well, if q is 0, it's trivial. You just get 0 unless p is also 0, in which case it's 1. If q is 1, it's just a single Riemann zeta value, so that's very easy. So if I just specialize this theorem, write EP2 for the coefficient, and just multiply out what I get, then for EP2 it's still very easy, EP1. By the time I have 2, I get a double sum, because I have P1 and P2 positive with sum P. So this thing is a sum which is the sum of Riemann zeta values, but it's got O of P terms, I mean P plus 1 terms. And similarly, when I go to EP3, and it gets worse if you continue, then you'll get 4/3 times the sum P1 plus P2 plus P3 is P of zeta of 2P1 plus 3, 2P2 plus 3, 2P3 plus 3, and then plus, and then there's a correction term, which is P plus 1 times P plus 2 over 3 times zeta of 2P plus 9. So now it's O of P squared terms. And similarly, if I take Q to be 4, I'll have O of P cubed terms, and so on. So I get more and more complicated formulas. But let's look at this EP2. I already mentioned that in the paper with Kaneko and Gangel, we had found that if you took the sum of the double zetas, AB, A plus B equals K, which is even, and if A and B are both odd or both even, then you just got 1/4 and 3/4 of zeta of K. But in the way to prove that, we also proved an identity for products of two Riemann zetas in terms of double zetas. And so that formula, which is very easy to show, shows that this EP2, which is here written in a way that's elementary because it only involves Riemann zetas, but it has lots of terms, it has P terms. But you can also write it with O of 1 terms. Namely, this thing is also equal to 2P plus 3 times zeta of 2P plus 6 minus 4 times zeta of 2P plus 5, comma, 1. Except that since it's 1, it means that I've, obviously on the day when I wrote this, the zeta functions were going the other way, because otherwise that would be divergent. So I better write it like that. So that's the perverse thing. Here we now consider this an improvement. In the previous story, the story with Ono, we had something involving multiple zeta values, or some combination of things involving multiple zetas, but then it was considered an improvement if that turned out to be polynomial than just ordinary Riemann zetas, because they're more familiar. But here we say this is an improvement because we have P plus 1 terms, but here we have only 2 terms. So if you continue this game, then you find that the same thing works for the higher EP3s. So for instance, this EP3, which here are P squared terms, will certainly have only 1 term. So here we had a term with zeta of 2P plus 9. Again, I'll have a term with zeta of 2P plus 9, but it's a different one. It's zeta 2P plus 9 times P plus 1 times P plus 3. And then it's minus 2 times 2P plus 5 times zeta of 1 and 2P plus 8. And then plus 2 zeta of 2 and 2P plus 7 plus 8 zeta of 1 and 1 and 2P plus 7. So one begins to see some sort of a pattern emerging. And so the statement is that any given EPQ has a formula which is only O of 1 terms. I mean, the size of O of 1, of course, goes up with Q. And I'm not sure I should actually write it down. If anyone's interested, I have it here. I think it's too much. There's a very pretty formula in which so in general, you'll get a formula where you have in front all possibilities with 1s and 2s. So here at the beginning we have either 1, 1, or we have 2, or we have a single 1, or we have the empty set. So in general, and the size of that is bounded. I mean here the size is bounded by Q equals 3. So the next time it'll be a little longer. I'll have terms, so the next one I'll have terms 1, 1, 1. So for E of P4, I'll have terms starting 1, 1, 1, 2, 1, or 1, 2, or 1, 1, or just 2, or 1, or the empty set. And then the last argument is whatever it is to make the weight correct, because the total weight is always 2p plus 3q. So here it's 2p plus 9. So if I have a 1, I have to have 2p plus 8. If I have a 1 and a 1, I have to have 2p plus 7. So in general, there's a formula of that sort, and the coefficients are some nice thing. And the proof is extremely cute, but I'll skip it. It's the same kind of idea that I used before, but somehow much trickier. You again make a differential equation, you get a hypergeometric thing, so the gamma functions come in, and then there's some amazing identity of binomial coefficients that you have to use that I'll skip because it's not worth giving it. And so we get finally we get this formula, but I won't give it because it uses the proof, which if anybody wants to see for purpose of technique, they certainly can have the thing which is written up. The proof uses all the same kind of things that we did before, differential equations, so hypergeometric and little gamma function expansions. But the amusing thing is here that we're running the machine backwards, as I say, and writing things that were already written in terms of Riemann zeta values, sort of perversely writing them back in terms of multiple zeta values, but in a much simpler way, and you get a very nice formula. So, and there's one other identity that I could have talked about and thought that I might. It's been talked about in these lectures, but from the point of view of its applications to the spectacular results that Francis Brown proved a year ago, and that was the evaluation of zeta 222, 222. And that proof, my proof was very sort of clever and ingenious. It took me weeks to work it out, and now there's a much simpler proof by Lee using ideas extremely similar to the ones that I presented here. So, well, I'd given a conjectural formula for these numbers that I first found numerically. It's the sum pi to the something times zeta of odd numbers times some coefficients. So I first found the formula experimentally, and then to prove it, each thing depends on two parameters, a and b, which are the number of 2's to the left and to the right of the 3, and here these coefficients depend on a and b. So you have some identity of the form h of ab and some h prime of ab, which is the conjectural formula. And to prove it, you make a generating function, some hab x to the a, y to the b, roughly. And what I did, that was very easy, was to show that each generating function could be given in closed form. One of them was a hypergeometric function, the complicated, an f32. But the other was a sum of terms, a sine function times a digamma function, psi of x is gamma prime over gamma. But the surprising thing was that one of the two generating functions was a single hypergeometric expression f32, but the other was a sum of 14 terms, each of which was a product of a sine function and a digamma function. So that looked extremely odd. And then the proof I gave was, I simply took these two things, I checked on the computer that they were really equal in various cases, so I believed it. And then I just checked that certain special values of these functions that I could evaluate in closed form were equal, and that the functions were entire functions of sufficiently slow growth that if you knew that they were equal at a large number of special arguments, that was enough. So it was an indirect proof. And now Lee gave a direct proof, and the idea is very similar to what we've been seeing. You use first the differential equation, well, that I'd already used to get the hypergeometric thing, and then you show directly that this hypergeometric thing, it has several arguments, and one of them, it's the limiting value as the argument goes to 0. And that limiting value, certain products in the limit when z goes to 0 turn into sums, and you end up indeed with the 14 terms, and it's actually quite short. The whole proof is now one page. Well, after my generating function, which takes a little work, but the proof that of the generating function identity. But it uses the same kind of ideas I've been sketching. So to summarize, there are lots and lots of identities among zetas. Conjecture, they all come from the double shuffle relation. We don't know how to do that at all. But at the level of the actual real numbers, the actual multiple zeta values, the technique which is almost universal, which works in almost all the examples I know, is that you replace the multiple zeta value by this higher polylogarithm. You use the inductive definition of this to get differential equations of various generating functions, and then you find, when you're lucky, that a generating function in t and further variables, where the further variables correspond to this index k, can be expressed in terms of hypergeometric functions. And now when you specialize to t equals 1 and use Gauss's formula, you're just left with things involving the gamma function, and that gets you back to Riemann zeta values. So I apologize for this extremely low-level talk that doesn't really fit such an august institute, but anyway, that's how it was.
Thank you very much. Any questions?
I didn't quite understand why you can't generalize this zeta of 1, 3, 1, 3, 1, 3. I mean, if I have, you told us if you have, say, you repeat a sequence, you will have a differential equation.
Well,
Perhaps you can't identify it.
Well, exactly, yeah, you don't
That's
know
all
what you
you,
have.
yeah. You
No,
don't know
but then you don't know what you have, so you just get that.
I mean, you
the
can write
answers-
down a differential equation, but then you don't know how to.
You don't know how to solve it.
Yes.
And there's no reason to think you can. And also, when you do it on the computer, I mean, this 1313, it wasn't inspiration, you know, that I just felt that 1313. In my tables, for instance, I had 1,024 values in weight 12. And most of them, in terms of my standard basis, were, you know, they had lots and lots of terms. And of course, one of my base elements was applied to the 12th. And then one of those zeta values, namely zeta of 1,3, 1,3, 1,3, was simply a rational multiple applied to the 12th. All the other 11 coefficients were 0. That simply never happens again, and there was nothing else you can recognize. So the problem is to prove identities. This isn't true, all of mathematics. Proving identities isn't that hard. It's finding identities which is hard. They don't grow on trees. And some of them do.
In this program, they do.
Yeah, maybe they do grow on trees, yeah. So that's indeed the problem, and that's sort of what I'm saying. If you have a plausible conjecture, then in principle you have a method of proof that it's always supposed to work. On the other hand, in the paper by Brothers and Company, you showed me that identity they had with more 1s and 3s and 2s, and they had an identity which they didn't succeed in proving, but they knew this technique because it was their technique on my slide improvement of it. And it's still hard work because in that proof it was 3 lines, but the main part was suppressed. I should have written, a little box. Lots of luck has to occur at this point, otherwise it wouldn't work. I mean, the whole proof is that both sides satisfy this. But already the fact that this thing factors in a nice way and that you can, I mean, of course if I took, let's say I did 1, 4, 1, 4. Then it would be exactly the same. To get from 1, 4, 1, 4, 1, 4 down to 1, 4, 1, 4 with 1 fewer 4, I have to go from 1, 4 to 1, 3 to 1, 2 to 1, 1, and then I subtract a 1, and then I subtract another 1. Okay, so here I have to apply t d by dt 3 times, and then 1 minus t d by dt twice. And so if I made the exact same thing with 1, 4, 1, 4, then here I would simply put a 3 and a 2 and a t to the 5th. End of the story, to the left-hand side. But now if you know the solution of that differential equation by heart, you just have to be lucky. And to me this is a totally amazing proof. I have no idea how Broadhurst found it. Well, actually he didn't, he found a more complicated version. I found this by simplifying what he'd done, but there's just a complete miracle here. You have to, well that's actually not true. I should have found the proof because after all, we know that it has to exist because the computer has already told us that there is an identity. There isn't one for 1, 4, 1, 4, but there is for 1, 3, 1, 3. So if you're simply brave, you say there has to be a proof, and the only way I can get at these numbers is by taking the polynomial, is that differential equation should be nice. So one day I look at it. And he just had the courage to actually do that, and it never even struck me that could work. I'd never thought of doing it by the differential equation, although I'd used other differential equations in a similar context. So, and the same, the Veneziano thing, I suppressed the proof. I didn't even write down the complete theorem, giving the final formula, but it's very pretty. And the proof is also completely amazing. But on the way, there are like 3 miracles. And each one is 1 line. You just go from one thing to the next, and it's trivial. Yeah. But if something didn't cancel, it wouldn't work, and then you couldn't proceed. And there's just a series of miracles, and you have no idea why it's working. So that's kind of the mystery of this whole field. We don't know how to write down relations systematically.
There is no general theory about the connection between polylog and hypergeometric equations. I mean, if you just
that's
have to be lucky.
That's a very good question. That's a very, very good question. As far as I know, no, there isn't. But it seems to be that if one dares to think in that level of generality, it might not be a poor idea at all. Of course, first you have to decide what you mean by hypergeometric, because already this wasn't actually hypergeometric, it was a product to hypergeometric. So, you can say, okay, you can express it in terms of hypergeometric things. And of course, hypergeometric isn't the alpha and the omega of all of differential equations. There are lots of other different, like the a priori type differential equations there are other differential equations that are not hypergeometric, but which can be solved in some sort of closed form and are sometimes related to things like modular forms. I don't know a connection. I'd be extremely happy if there were a non-hypergeometric differential equation of the modular sort, the sort that comes when you expand the modulus in a modular function. If such differential equations, I don't know. So probably the answer is yes, there's a much deeper connection. Because sort of what I've been saying in this lecture is, look, gee, every time that one does one of these calculations, it uses a new variant of the same idea. So it's very unsatisfactory. There must be a reason why the same type of calculation of hypergeometric thing keeps recurring. And I have no idea what it is, because each time you have to be lucky, and there's no way to produce the luck for the next time. So it's a great question. Yeah.
Other questions? If not, let's keep going.